Good morning. We are moving on into chapter 41. We are going to be looking at nuclear physics, so it's the physics of the atomic nucleus. We've got this chapter and chapter 42, so there's a good amount of coverage on these topics. So let's familiarize ourselves too with the nucleus. And so, we think of the nucleus as being made up of protons and neutrons. I always feel like what gets left out here is the nuclear force. The nuclear force is a major player here in terms of how it's holding the protons and neutrons together and the effect it has on the properties of the nucleus. So we want to be able to keep that in mind. So they're just putting out some basic properties here for the proton and neutron. They're giving us the mass of, I think this one should say mass of the proton, not neutron. And then this is the mass of the neutron. And the thing that stands out here is that the masses are so similar. And what we're going to find out is protons and neutrons are in some ways, they're kind of the same particle. The proton is the positive version of that particle, and the neutron is the neutral version of that particle. So their structure and their properties are very similar. All right, again, this is mass of the proton, so in your notes when you take a look at this, make sure that gets listed as proton. They got a lot of significant figures on some of these numbers. And I think that's pointing out that we've made very, very careful measurements of these values. All right, so in terms of the structure of the nucleus, a couple things to keep in mind. Protons and neutrons together are referred to as nucleons, which is kind of an interesting word that they've come up with. So a lot of times when we're looking at the nucleus, we're talking about how many protons there are, we're talking about how many neutrons, but it's also important to know what's the combined total number of protons and neutrons. So it's useful. So I think what they have here is number of protons is referred to as the atomic number, and for the atomic number we use the symbol Z, capital Z. And then the number of nucleons, the number of protons and neutrons combined, is referred to as the mass number, or the atomic mass number, and that gets the A. So a little confusing. I don't know if you want to think of those as mnemonics or just memorize that Z is atomic number, A is the mass number. Now the neutron number they have listed here, if we take the total number of nucleons, subtract out the protons, whatever is left, those are the neutrons. So this chapter also introduces something called the neutron number, which is handy also. So for any nucleus, we can talk about how many protons are in there, that's Z. How many neutrons are in there, that's N. And then N plus Z combined equals A. And a couple things to keep in mind here. The atomic number Z tells us which element it is. So we classify nuclei based on how many protons are in the nucleus. It's the number of protons in the nucleus that determine the chemical properties of that particular element. So Z is also telling us where we're going to place this on the periodic table, tells us which element we have. And again, I think we mentioned this in earlier chapters, but it's the number of protons in the nucleus that determine how many electrons will be attracted, and those electrons are going to form the chemical bonds. So it really does. The element characteristics trace back to the number of protons in the nucleus. Neutrons add mass, but they don't change the chemical properties. So however many number of neutrons are in the nucleus, that doesn't have an effect on which element it is. Now the symbols, the pattern that we use to represent different elements are these. So a particular isotope of an element is listed based on its chemical symbol, and then in the lower left we put the number of protons in that nucleus. In the upper left we put the total number of protons and neutrons, which gives us an estimate on the mass for that isotope. Let's look at some examples. It's easier to see what this is referring to. So nuclei with the same Z value are called the same element. If they have variations in numbers of neutrons, those are referred to as isotopes. Most elements have some number of isotopes. In fact, if you look at kind of the mid part of the periodic table, some of those elements will have 30 or 40 different isotopes that have been identified. So this wide range of neutron number. And of course, a number of those have just been identified in laboratories. So naturally occurring isotopes are maybe only a few per element. But we've been able to create and identify a wide range of isotopes in laboratories. All right, here's a quick diagram. So here's an example of different isotopes of hydrogen. So hydrogen, we have the chemical symbol H. Now, any nucleus that has just one proton is classified as hydrogen. So a proton, all by itself, is classified as being hydrogen. The symbol we would use for that, here's a proton all by itself. It falls into the classification of hydrogen. It's got one proton, and combined, it's got one proton, total protons and neutrons together. So, you know, a proton all by itself has this notation to it. Now, there's a heavier version of hydrogen, there's a heavier isotope that has one neutron. And so the symbol for that, we still use the same chemical symbol. It's still hydrogen, it still forms hydrogen compounds. It still has one proton. So what we're seeing here is this is really redundant in that the chemical symbol is always going to match to a certain number of protons. But it's the notation we use, and this ends up just being a reminder then of how many protons there are in that particular element. And then there's an even heavier version of hydrogen with two neutrons. One proton again, because hey, it's hydrogen. And we put the 3 up there to say that we have 3, the total number of protons and neutrons is 3. Now that upper left corner is referred to as the mass number, because as we saw in that earlier, in the earlier slide, protons and neutrons have very similar masses. And so what we can do is we can very roughly, we'll assign one atomic mass unit to be roughly the mass of a proton or a neutron. And then by counting the number of protons and neutrons, that'll give us the mass of that nucleus in terms of atomic mass units. And that's handy because that'll give us integer numbers. So for example, the mass here it's pretty close to about 1 atomic mass unit. The mass for hydrogen 2 is about 2 atomic mass units, and for hydrogen 3 is 3 atomic mass units. Now the isotopes of hydrogen we refer to those so often, we've actually given them names individually. So we call this version of hydrogen, just the proton by itself, protium. And hydrogen with an additional neutron attached is deuterium. And hydrogen with 2 neutrons attached is referred to as tritium. So protium, deuterium, tritium, those are the 3 isotopes for hydrogen. Now just to see what another element would look like, I moved one more step into the periodic table, and what we have here is helium, and helium is element number 2, so it's got 2 protons, And the particular isotope that I've drawn here has 2 neutrons also. Helium has a helium-3 or a helium-4 isotope that are both. The helium-4 is by far more common, but the helium-3 does exist at a lower abundance, naturally occurring. All right, so hydrogen 1, 2, and 3, helium-4. Let's look at something more complicated here. Iron, here's an iron 56 symbol. So the Fe stands for iron. The 26 in the lower left corner says, hey, that's the number of protons that iron has. So any nucleus with 26 protons in it is going to get classified as iron. The 56 is the combined number of protons and neutrons. So that would say that iron 56 has 26 protons because, hey, it's iron, and 30 neutrons makes up the difference between those two numbers, and we would refer to that as iron 56. Now, another thing I should point out here is when I'm drawing these different diagrams of the nucleus, nuclei often get written as these little spheres that are all kind of glued together or something, and we want to think of them as being more dynamic than that. That they don't, they're going to be represented by wave functions. So the same thing that we saw for electrons. Electrons aren't just a solid piece of something. It's like a little marble or something that's following a trajectory. The electrons are being represented by wave functions. So are the protons and neutrons. So we haven't drawn them that way, but there are equivalent to, for example, 1s states for the proton, 1s states for the neutron. So in something like helium-4, for example, there's a 1s state for the equivalent of a 1s state for protons, and helium has a spin-up, spin-down pair of protons in that 1s state. And then the neutrons, also there's 2 neutrons, in a 1s state, spin up, spin down, and helium-4 is especially stable. When you have a pair of protons, pair of neutrons in this lowest possible energy state, any additional protons and neutrons would have to move up to a higher energy state. So we want to remind ourselves that the protons and neutrons have wave functions in the same way that electrons do. And again, the key item from here is being familiar with different isotopes of different elements. Now, as far as the size of a nucleus, remember, since these protons and neutrons, they're going to be understood in terms of their wave functions. And those wave functions are going to spread out a certain amount. As we put more and more protons and neutrons into a nucleus, the wave functions overlap with each other, same as the electrons did. So we're getting overlapping wave functions. But the wave functions do tend to take up more and more space. They're not as tightly compressed. So we had mentioned, I guess we should go back and take a look at this too. We said that the nucleus is more than just its protons and neutrons. It's the nuclear force holding everything together. So there's an attraction between all of the protons and neutrons, and it's based on this nuclear force. In particular, it's the nuclear strong force holding these protons and neutrons together. So, from the word strong, you kind of get the idea. This is, it's a really strong force, but it's only a short distance. So, which is good. If we have the nuclei that form these very tight bundles of protons and neutrons, but other nuclei are far enough away that not all the protons and neutrons in the universe have all collapsed into one big nucleus. So these nuclei have very strong forces within them, but once you get a little ways away from the nucleus, the forces drop off very rapidly. So they're only short-range forces. So those very short-range nuclear strong forces are holding the protons and neutrons together. Think of this as a bunch of overlapping wave functions. And if we do a series of experiments, it says this is through electron scattering, we can come up with kind of an empirical formula as to what's the size, what's the diameter, the volume, or in this case it's the radius of a nucleus. And to a good approximation, we can model all of the nuclei through the periodic table as having a radius of 1.2 10 to the minus 15 meters times a to the third power. Now, if you remember, a was the mass number. It was telling us how many protons and neutrons there are. And so, if this was hydrogen 1, protium, I could put a 1 in for a, and that would say that a proton all by itself has kind of an effective radius of 1.2 10 to the minus 15 meters. And that gives us an idea of how spread out the wave function is. Now, comparing that with the size of an atom, a hydrogen atom, we would say, has a diameter of maybe 100 picometers. Well, this is down at the range of a femtometer. So 1 femtometer versus 100 picometers, that's like a distance of 10,000 in terms of distance. So there's quite, or 100,000 in terms of distance. That's quite a big difference. The nuclei, you always say if you're sitting in a room, a good-sized room, and you think of the room as kind of being the size of the electron distributions, that the nucleus would be a tiny speck at the middle of the room. You would have to actually look hard for the nucleus in that room to be able to find it. So that's tiny. 10 to the minus 15 is femtometers, and so we're going to be seeing the use of femtometers more and more in our discussions. And that's kind of what this slide is referring to. Also, nuclear versus atomic sizes and densities. So how dense is that material? And here's an example. So what we've got is this effective nuclear radius formula that we just introduced. R is equal to R naught, a to the 1/3 power, where R naught is 1.20 femtometers. Now what we can do is, so we're going to remind ourselves, A is the number of nucleons. So however many total protons and neutrons are in there, that's what goes in for A. And then what it's saying is that, what we're going to show here is that this predicts that each nucleon can be thought of as contributing a certain amount of volume. So if we take that standard radius and plug that into a sphere formula, we can say that that amounts to about 7.24 cubic femtometers in terms of volume. Now, the reason we're stating that is that, well, let's take this formula where we have a to the 1/3 power. Let's turn that into a volume. If we say, well, what's the volume then for a nucleus? What's the effective volume? How much space does that nucleus fill up? We can write that as 4/3 pi r to the third, and then we'll substitute for the r, we'll substitute in r naught, a to the 1/3, and by cubing the big A, then it just becomes 4/3 pi r naught to the 3rd power times A. And we can take all of the stuff inside here and say that's the effective volume of any individual proton or neutron. So if we add together all of those, then the total volume is equal to this fundamental volume times the number of protons and neutrons. So in some sense, we can say, kind of to a good approximation, each proton or neutron contributes equally to the volume of a nucleus. Now, let's take that a step further and think in terms of the densities that we might be coming up with then in this case. So think of the planet Earth. So planet Earth it's pretty big. It's a good sized planet. And it has a mass of 6 times 10 to the 24th kilograms, and it has a diameter of 12,700 kilometers. So it's about 8,000 miles of diameter for the Earth. Now, the mass of an individual proton or neutron is 1.67 10 to the minus 27. And again, the proton and neutron masses are so similar to each other that to a good approximation we can just kind of pick an average value or an estimate that applies to both. And what that says is that the number of nucleons in planet Earth can actually be determined. Now you might be thinking, well, what about all the electrons? Don't we have to include the electrons in this calculation? And we really don't. The electrons make up less than 0.1% of the mass of materials around us. And so the electrons can pretty much just get ignored in estimating these numbers. And we can say that the number of protons and neutrons in planet Earth, 3.6 10 to the 51. So now 10 to the 51 is not a number we encounter often, but it's an enormous number. 10 to the 51 is really big. All right, so if we've got that many protons and neutrons that make up Earth, and Earth currently has this diameter, what is it that's taking up most of that volume? Is it the protons and neutrons, which are making up most of the mass, or is it the electrons that are taking up most of the volume? And if we think back to chapter 39, looking at atoms, we'd say, hey, it's the electrons. When we look at atoms and molecules, the electron wave functions are spread out. You know, they cover hundreds of picometers. And we said, you know, the nuclei are little tiny point charges within those electron distributions. So the electrons are big and bulky, and gravity's pulling the whole planet together. But the electrons are about as tightly packed as they're comfortable being packed. Now, what would happen if somehow magically we got rid of all the electrons and we were able to take all of these protons and neutrons that make up Earth and pack them all together into just one nucleus? What if we took all the nuclei on Earth and combined them into one gigantic nucleus and ignored all of the volume effects that the electrons take up? Well, we could do that. What we could do is say, if we took all the protons and neutrons and just packed them into one nucleus, each proton or neutron would be taking up 7.24 cubic femtometers. So to get the volume of this nuclear Earth, we could take the volume of each neutron or proton, multiply that by the number of protons and neutrons, and that would give us 2.6 10 to the 7th cubic meters. And then using the formula for a sphere, that would actually give us a radius of less than 200 meters, a diameter of 364 meters. So if all the protons and neutrons that make up the Earth were all compacted into one smaller sphere, one nucleus, it would only have a diameter of 364 meters. Okay? Not very big. That's quite a compactification. Now you might ask, well, at that size, how much mass would it have? And its mass would pretty much be the same. The mass, again, would be a very small, negligible effect if we just remove all the electrons. The electrons don't contribute that much to the mass. So kind of interesting that in atoms and molecules, and the mass is packed into these little tiny nuclei, And the electrons end up being big and bulky and taking up most of the space in the materials around us. Now you might ask, well, are there any, and I drew these spheres, they're not to scale, I don't know why I did this. So, you know, here's this enormous planet, and then it now is just represented by something a few hundred meters in diameter, and that's it. Are there any objects like this in nature? And there are. They're what are called neutron stars. Neutron stars are stars that have gravitationally collapsed. They've gone through a supernova explosion, and through a reaction that we'll actually see in this chapter, the electrons and neutrinos, the electrons within there have been turned into neutrinos, and the neutrinos have separated away from the star. And so all that's left are neutrons. The neutrons compress to a really small diameter. With all the electrons gone, all those big bulky electrons gone, the star now is gravitationally compresses down to a much smaller size. All right. Now, in order to measure the masses of nuclei is really what we want to think in terms of, and atoms are kind of the same thing. So when we're measuring these masses, again, most of the mass is due to the protons and the neutrons. The electrons add a little bit on, and they're going to be measurable. We're going to have to keep track of the electrons and be clear when we're including electrons, or maybe when we aren't including electrons. We've set up a reference scale, and we had to pick one particular isotope. So the isotope that got picked was carbon-12. And carbon-12 is designated to have exactly 12 atomic mass units. Now that's not just the nucleus, it does include the electrons. So a neutral carbon-12 atom, by definition, has a mass of exactly 12 atomic mass units. Now you might be thinking, well, why didn't we just start with a proton or a neutron and designate one of those to be one atomic mass unit? And that turns out not to work, because as we add more and more protons together, there's actually a mass effect from the nuclear force. And so we can't, it's not as simple as just adding the number of protons and neutrons together and finding out what their mass is. That gives us a good estimate, but it doesn't give us the exact value. So again, we're going to use carbon-12 as our reference. That's 12 atomic mass units. Just so that we know the conversions here, 1 atomic mass unit, 1.66, 10 to the minus 27 kilograms. That's going to get used some. And then what we're probably going to be using even more is that 1 atomic mass unit has an energy equivalence of 931.5 MeV. So I know the textbook likes to put this over c squared and remind us that we actually need an mc squared to carry out this calculation. But what we'll find in our calculations is, for the most part, we're just doing this straight conversion. I know that if I have a certain number of atomic mass units, that's going to be equivalent to a certain amount of energy. So that 931.5 MeV is going to show up a lot. Now, here, we've got a mass table. It's good at this point, I think, to sit down and go, okay, here's the electron, here's the proton, here's the neutron. They even put the hydrogen atom in here just for comparison. But what they've done is they've listed the masses of our fundamental particles, the electrons, the protons, the neutrons, and they've listed those in terms of kilograms, and they've listed those in terms of atomic mass units, and they've listed those in terms of MeV. So here is the MeV, and we've been working from these, 0.511 MeV for an electron. Here are the MeV values for protons and neutrons. So 938.3, 939.6. In terms of atomic mass units, you can see that the proton actually is more than just one atomic mass unit. It works out to be 1.007276. For the neutron, it's 1.008665. And that's saying that once we've determined that it's carbon-12, that we're going to base the atomic mass system on, then these are the values that the proton and the neutron have. So you can see those are a little different from one. They're similar, but they're, you know, close to being 1% above what that one atomic mass unit. All right, and what you also are starting to see here is that we're keeping a lot of significant figures in some of these calculations. And for those of you who, for 3 semesters now, all the way through Physics 4A, 4B, and now in Physics 4C, have really wanted to be able to write down 6, 8, 10 significant figures on a problem, this is your chapter. Because it turns out, as we'll see, many of our calculations require us to come back and write down these mass values. For example, with these atomic mass values here, those are 7 significant figures. We're going to need all 7 of those in many situations, and we'll see. All right, let's start talking then about binding energy. How much energy is associated with the nuclear force holding the protons and the neutrons together? So it says, for example, let's take helium-4. We had mentioned that helium-4 is an especially stable nucleus as well as an especially stable element. Or atom, I guess is what we want to call that. So as a nucleus, it's got 2 protons that are spin up, spin down in a 1s state. And it's got 2 neutrons that are spin up, spin down in a 1s state for neutrons. And it's got 2 electrons that are in a 1s state, spin up, spin down. So all of that is keeping the pairs of protons, electrons, and neutrons in their lowest possible energy state. The size of those wave function extensions are really tiny for the protons and neutron pairs, and then the electron is much larger. So if you think of a bunch of 1s wave functions, 3-dimensional 1s wave functions, for protons, neutrons, and electrons, all overlapping, that's our helium-4 atom. So let's take a look at the individual pieces that make up helium. Now we're calling this nuclear binding energy. So if I take a look at helium-4, it's got those 2 protons, the 2 neutrons, the 2 electrons, and what I've done is I've taken the masses for the protons, neutrons, and electrons in atomic mass units. Now I drew kind of a dashed line here because we're looking at the nuclei is what we're really interested in, but in many cases it's more convenient to measure masses, just bring the electrons along. Don't just measure the nucleus, let's measure the completed atom with its electrons. So that's what we've done here. And when we do that, if we take the mass of 2 protons, 2 neutrons, 2 electrons, those add up to 4.032979. They're the significant figures. If we look at the mass of helium-4 once it has formed, the numbers don't match up. And what we're seeing here is mass is not conserved. So even though we have this much mass in the protons, neutrons, and electrons, when they combine to form helium-4, some of the mass is missing. We don't have as much mass as what we started with. So what's going on here is primarily the nuclear force. The nuclear force is so strong that we're actually seeing how it affects the mass of this nucleus. So we can actually carry out a calculation. We can say individually the protons and neutrons and electrons would have this much mass, but due to the nuclear force primarily, it's got a less mass. There's missing mass taking place. And so I can subtract those 2 numbers. Now what happened was, since this number and that number were actually really quite similar, I needed a lot of significant figures to be able to subtract them. And what I ended up with was 0.030376. Now what we're going to do is, that's a certain amount of mass that's missing. Let's find out how much energy that corresponds to. And here is our conversion factor that we mentioned earlier, that every time we see an atomic mass unit, in terms of energy, that's the equivalent of 931.5 MeV. And so what we found is that for this helium-4 example, we have what's called a nuclear binding energy of 28.30 MeV. That's a lot of energy. 28 MeV of energy is pretty significant. Now, what we can also do is say, well, kind of on average, how much binding energy is there for each one of the nucleons? If we think of a certain amount of binding energy and divide it by the four protons and neutrons, the nucleons that are in there, then per nucleon, that's 7.074 MeV. So we could kind of think of it this way. Each proton or neutron has a binding energy of, a little over 7 MeV. What does that mean? Well, it means this. It means that during the process in which helium-4 is formed, nuclear fusion reactions, there's a series of reactions that would have to take place. So protons and neutrons would have to be brought in and combine. Every time we bring in additional proton or neutron, a lot of energy is released. These are exothermic nuclear reactions. So the fusion processes that take us from 2 protons and 2 neutrons to helium-4 end up releasing that much energy. It's an enormous amount of energy to be released. And so what happens is, well, if that's the energy that was released during the formation of helium-4, how much energy would it take to take a helium-4 nucleus and separate it back out into its individual pieces? And that's it. That's the binding energy. That's how much energy would have to be brought in to the protons and neutrons in order to take that nucleus apart. All right, so these are numbers that you definitely want to be able to calculate. You want to be able to start with masses of protons, neutrons, and electrons. I've got those programmed into my calculator so I can just pull them up, and they've got 9 significant figures on them, and I don't have to worry about hitting the wrong number and making an error. So I double check those, put them in my calculator memory, pull those up quickly, and you should be able to use those to determine these numbers. Just for comparison, let's do another nuclear binding energy. Again, these are kind of interesting problems. Let's try carbon-12, for example. So to form a carbon-12 nucleus, I've got 6 protons, 6 neutrons, and then we'll throw in the 6 electrons, and that gives us a combined mass 12.098940 atomic mass units. Now, by definition, the carbon-12 it only has 12 atomic mass units of mass. That's it. And so we clearly have mass differences. There's definitely a missing mass taking place here. If we take this amount of missing mass and use our 931.5 conversion, what we find is that the combined nuclear binding energy for carbon-12 is 92.16 MeV. Now, that's quite a bit bigger for helium-4, but maybe that's not a fair comparison, because it's not quite a fair comparison because the helium-4 only has 4 nucleons and the carbon-12 has 12 nucleons. So what we do is we do that per nucleon again to do kind of a side-by-side comparison, and it looks like I didn't quite get this included. So this worked out to be, when we divided through by 12 nucleons, came to be 7.68, or what those numbers are. Or you can double check and run those calculations. Definitely run both of these examples. run through them on your own, make sure that you're really clear. So then we can do a more reasonable sort of side-by-side comparison. We can say that nucleon for nucleon, carbon-12 is just a little bit more stable than helium-4 because the binding energy per nucleon, 7.68 versus 7.07. So that becomes a handy way to kind of judge one isotope versus another and say which one is overall more stable. Okay. So a couple things to keep track of in these calculations. So whatever isotope we look at, the total mass of any nucleus, not just the stable ones, but also the radioactive ones. So I guess that means it's still stable. Any nucleus that we've identified, the masses of those nuclei are less than the mass of the protons and the neutrons. Where did the mass go? It's become kinetic energy. So during a process in building those nuclei, a lot of energy was released as either kinetic energy, maybe it was released as a bunch of photons, but the energy disappearance reduces the mass of those objects. Now at this point you might be thinking, well, does that happen in a chemical reaction? In chemistry, we assume that the mass is being conserved. In chemical reactions, the masses definitely change. So there is if it's an exothermic reaction, there's a little reduction in mass. If it's given off energy, then the mass has gone down. If it's taken in energy overall during the reaction, the mass has gone up a little bit. But in chemical reactions, the differences are so tiny, they're virtually immeasurable. So in chemistry reactions, to a good approximation, we can use conservation of mass in determining product yields. In nuclear reactions, we just can't do that. The amount of mass variations that take place are starting to become, maybe 1% of the overall mass. Our calculations could be way off. So we've got to include those mass differences that have been taking place. Now another thing to keep track of here, how do we include the effect of the electrons? Now we're calling this nuclear binding energy. There's just a little bit of electron binding energy that's included here. There's an electromagnetic force holding the electrons in place. That also affects the mass, but only to a much smaller effect. The way dominant effect here is the nuclear binding energy, and so we don't worry so much about that small difference that is included from the electron binding. All right, if we look through the periodic table, what we find is along this horizontal scale, this is number of nucleons. It's the mass number. And what we're doing is looking through the periodic table as the mass number goes up. And we're starting off with, elements like, or isotopes, like hydrogen-2, helium-3. Helium-3 is not especially stable. Ooh, but look at helium-4. So what we're doing is looking across the periodic table and saying what happens to the nuclear binding energy, kind of on average, as we look through the periodic table. And what we find is that helium-4 is kind of our first example of a really stable nucleus. We've got 2 neutrons and protons packed in those lowest quantum states, the 1s states, that we've been talking about. And so already we're up to 7 MeV per nucleon. Now a couple of other notable, really stable elements here. They've listed oxygen. Oxygen takes us up to about 8 MeV per nucleon. And then you'll notice the very most stable isotopes, of all the isotopes, of all the elements in nature, the most stable nuclei are in this region. And they've picked out what is often considered the most stable isotope in terms of just nuclear binding energy, and that's iron-56. So iron 56 has one of the very highest binding energies per nucleon. And notice that it's about, it's about 8.7 or 8.8. So those are the most stable. What that lets you know is that if you're doing a homework problem or a midterm problem or something, and you're getting binding energies above 9 MeV per nucleon, something went wrong. Because even the most stable elements have binding energies of about 8.8. That's about where it tops out. Now, as you continue moving the periodic table, here's an isotope of tin, and that's tin 120, and you can see that the binding energies per nucleon are beginning to drop off as you go farther and farther through the periodic table. So what it's saying is this, and this is kind of looking ahead to the next chapter, but it says that when nuclear reactions take place, either in, well, nuclear fusion reactions, say inside stars or something, or nuclear fission reactions inside power plants, what's going on is this. If I've got a power plant that's running on uranium, uranium has a binding energy, per nucleon of 7.7 or something. When I split that uranium, it splits into two things that are kind of, half the size of what that uranium was. And those are now going to have much higher binding energies. So kind of the optimal size for a nucleus in terms of binding energy is here. And as the nucleus gets larger and larger, that nuclear force is not able to extend as effectively over a large nucleus as it does over a smaller nucleus. So you can actually release energy. Our fission power plants are taking nuclei that are bundles of protons and neutrons over here. It's actually not the 238 isotope, it's 235 isotope of uranium. Splitting it into pieces, and there's a huge release of energy because of the more effective binding energies that can take place with two smaller size pieces. So that's nuclear fission on this diagram. The other direction on this diagram is if we just start off with protons and start fusing them together to form these different isotopes of elements, there's going to be an enormous energy release there. So nuclear fusion, these are the reactions going on inside stars. We build up deuterium, isotopes like helium-3, helium-4. If you're familiar with fusion reactions in stars, most of the star's lifetime is fusing hydrogen into helium. Our star, the sun, its energy source is from fusing hydrogen into helium. And you can see how stable helium is, so that's a huge amount of energy that's released. Now, heavier stars are going to be able to fuse heavier elements. We're expecting the sun eventually can form elements like carbon and oxygen. Even heavier stars are able to fuse elements all the way to iron. But once the fusion reactions reach iron, there's not going to be a release of energy from those reactions. Those reactions now are going to require energy to operate. So very generally, fission starts with heavy elements, splits them into lighter elements that have higher binding energy per nucleon. Fusion reactions build up heavier and heavier elements from the lighter ones. Again, this direction, anything heading in towards that kind of iron 56 location is going to release energy. So two possible forms of nuclear energy. Here it says, the next problem they suggest that we carry out here, total binding energy for iron 56. So let's go ahead and take a look at that. So, and we've done a few of these, so we can step through this a little faster maybe. So for iron 56, I want to identify it as having 26 protons, 30 neutrons, 26 electrons. I carefully enter all of those significant figures into my calculator, and I ended up with this as the combined mass of all those protons, neutrons, and electrons. Then I look up the completed iron 56 isotope. Now, where these values are, you might be thinking, well, where do I look something like that up? Where do I look up the mass of iron 56? And it's in Appendix F in your textbook, or else go online. You can't use a periodic table for this. A periodic table gives you values averaged over the isotopes for a particular element. But we need one particular isotope. And so the periodic table is not going to give you those numbers. You've got to look up an isotope table that gives you individual data. Again, go online or in your textbook, flip to the back, find Appendix F. Appendix F is your friend. You're going to want to reference that pretty commonly. If you do go online, Wikipedia has an excellent set of articles. For each element, they have an isotopes of article. So isotopes of iron will list all of the isotopes that have been identified for iron and all of their masses. Isotopes of tin, isotopes of palladium. So whatever the element is, you can look those up on Wikipedia also. Appendix F is not complete. It doesn't have all the isotopes of all the elements. There's thousands of isotopes that we have identified. All right, we're going to take the missing mass from this, use our 931.5 conversion. That gives us 492 MeV. Now, that's total binding energy. We want to divide through by the number of nucleons, and when we do that, we end up with this value of 8.790 MeV per nucleon. All right. Okay. I slipped in one more example. Do we want to look at this? Sure. We'll stop right there. I think it's a good time to take a break. So I'm going to stop there and then we'll pick up in the next lecture. We do have a couple more examples here with binding energy that we want to take a look at.